or more precisely, giving access to HPC data into the cloud. Roughly what I'm talking about. What's the problem that we're trying to solve here? How are we doing things now? And we are doing it. How can we actually do it better? And can we do it even better when future developments in Lustre happen? And in conclusion, I may be the only person presenting a talk in the last 2 days who's not going to talk about performance, because ultimately this gets down to NFS gateways, and performance is not really an option there. Certainly not HPC. So, yeah, I'm not talking, tens of gigabytes per second unless someone really tries hard. I'm talking much less than performance. So I'm not even going to talk about it, really. So, the problem we have is we're all working in high-performance computing, and that basically means big collections of data, workflows that ingest large quantities of data and spit out large quantities of data. That's great. The problem is really big quantities of data end up sitting in silos. We have a big silo over there. I think Daniel was talking about 22 petabytes or something like that. I know Aussie has a large silo over there. Basically, any place that does HPC will have a big collection of data. And it's generally sitting in something like a Lustre file system, and it's generally really hard to get access to outside of the context of the HPC system which it's connected to. Now, the researchers who produce that data want to share it. They want to collaborate. They want to collaborate with people overseas. They want to collaborate with colleagues from different institutions, and they want to do things like post-processing. They want to look at little bits of the data and decide what to do with it, or determine the meaning of it, or something like that. They want to make it available for ad hoc user post-processing. We have virtual desktop infrastructure at NCI, which basically allows you to log in and get a desktop, essentially, that's in the cloud, and provides you with access to the major data store. And there's even things like running a citizen science program, where a piece of software basically takes a chunk of data and then presents it to some random person on the internet. They do something with it, and then they come back. That kind of data access is increasingly being requested by the researchers. The other thing is the researchers really don't want to be tied down to a system that's run by an HPC admin. They want to be able to install their own software. They want to be able to run things on their own time frame. They want to do development themselves. And basically, they really just don't want to be waiting on us. They want to do everything themselves, or as many things as possible themselves. So the solution to that is cloud connected to, or loosely connected to the HPC. The problem with that is that cloud environments are really, really insecure. In theory, you can probably harden them down and make them actually, secure. I know VMware says that. In practice, most of the time, the people who run the instances in the cloud are not experienced admins. They're not malicious, hopefully, but they're not necessarily going to avoid the RN-RF slash RN-RF /star. The standard fumble fingers mistake. They're also not going to harden their instances, which means that as soon as they make them available on the internet, you really have to assume that they're going to be owned. Even if they're not, you still have to assume they are because of the paradigm. The other thing is, the virtualization stack itself isn't particularly secure. There's been basically a long stream of vulnerabilities where someone who can run some code inside the guest and break out of that guest and run arbitrary code on the the hypervisor. At which point the hypervisor is owned. And because this is a cluster, there's a web of trust between the instances, between the hypervisors. So a lot of them have SSH trust between them, at which point the entire cloud infrastructure is owned. So basically, you don't want to give access to your multiple petabytes of data to something that could be owned by a completely malicious third party. Now, you really don't want to do that with Lustre, because Lustre just assumes that it's a trusted environment. There's no option to root squash or any equivalent, though there's work being done on that. You can see any user who can mount the file system can see the whole file system. And again, there's a bit of work being done on that. Some of the future stuff I'll get to later. And there's very little that's actually enforced at the server side. So things like the subdirectory mounts are client side and so on. And you really need to have a wall of trust. On one side, you can't trust anything at all. On the other side, you're enforcing constraints in order to be secure. So, how do we provide access? Now, a bit of context. This is a rough description of the insecurity network architecture. The interesting bit is the green line joining the OpenStack partner and the green FDR IV fabric, which connects to GData. GData is the crown jewels. The OpenStack partner is our partner cloud. Now, there should be a box there that says NFS Gateway, because that is the solution. Our data storage team runs an NFS Gateway. It can be scaled up. They mount Lustre on one side, and on the other side, they provide NFS exports. It's manually done, so whenever a user wants to export a chunk of the Lustre file systems, they go to data storage and they say, can you export this? Can you export it to this IP address? And then an admin goes in, edits the exports table, voila, done. That's admin heavy. It's waiting on someone who has the right to go in, the permissions and everything to go in and update the NFS gateway. And it's really not dynamic because, again, you're waiting. And the users really don't want to be waiting. Now, as far as the implementation goes, we do per project exports. So basically, projects have a subdirectory within Lustre, possibly a few more, and we essentially export that subdirectory. It's exported with all squash, with the non-UID and the non-GID set to a per project service account. So an account that actually is a member of the project, which means that it has access to the right bits and doesn't have access to the wrong bits, and you end up with a consistent set of permissions and so on. It's not particularly dynamic or flexible or anything, but it works. And from an admin perspective, it's a little bit painful, but it works. When I put my cloud hat on though, that really sounds like it hurts. Because cloud is really dynamic. The whole point of cloud is that users can create and delete instances, they can create and delete their own virtual environments, they can create and delete development environments, production environments. It's all very, very flexible. If you want to do the manual process of modifying exports and so on, you have to either put an enormous amount of work in order to be reasonably responsive, or you lock the clients down and basically say, so you can only do anything with this like this, lock it for IP addresses, or something like that. So it's that traditional systems administration process fighting with the user's expectation of the cloud. So how can we make that better? Enter stage left OpenStack Manila. It's basically a shared file system as a service project. So what it is infrastructure that allows users to request the creation of a shared file system on the fly. The users manage access to it, they can create and delete it and so on. Aside from setting up the infrastructure and setting up the actual backend storage, admins have very little involved in it. It can be extremely dynamic, so it can be as dynamic as a storage block is created in the cloud, and then a server is created in the cloud, and a network is created to hook up that server to your instances. Everything happens essentially by magic in the cloud. It can also be quite static, so you can actually set up a server so that instead of creating a server on the fly, it actually runs some code on, say, our NFS gateway. So the overview of the architecture of Moonlight, it's quite similar to a lot of OpenStack projects. It's quite loosely coupled. You have an API server, which is what the user connects to, the user talks to. It's an HTTP server, basically, that an HTTP application that responds when the user just does a GET, POST, etc. That then passes these requests onto a scheduler, which knows about all of the backend services that are there, all of the storage services that are there, and it goes, okay, so you've requested from share here, we'll go and do it, go and talk to that backend. And then there's the backend share service, which is the thing that actually manages the resources. The way that this is put together means that the backend is really the only thing that needs to change, assuming the API is capable of expressing what you want it to do. That's the bit that we've been working on. You can have many backends. So you can have 15 different NFS servers, each exporting different things, and each one has their own backend. The scheduler knows about each of these backends and sends requests to the appropriate one. You can also have multiple different resources being managed. So it doesn't have to be one of our gateways. It can also be a SecFS set up in the cloud. It can be a Cinder volume-backed shared server set up entirely in the cloud. And so you can actually integrate a number of other services, a number of other requirements into this same architecture. And there's a common thing in the cloud. Being an OpenStack project, it integrates quite nicely into OpenStack. It uses the same OpenStack authentication system, Keystone. You can use the OpenStack dashboard to manage it, as well as using OpenStack client libraries and so forth and tools. And it gives you a quite consistent user experience, and one that matches users' expectations of cloud. So how does it actually, what's the actual processing? The user starts out by saying, I'd like to make a new share. That goes to the API server. And the request is essentially create a share, exporting these resources. The scheduler goes, oh, that looks like it belongs on that NFS server, and it forwards the request onto the back-end process that's running on that NFS server. The back-end does sanity checks. So if you're asking for access to data owned by Project Foo, and you've logged in as Project Bar, then it may well go, no, you don't have access to that. 404. Assuming that the request goes ahead, then it decides what user ID and group ID to squash the access to, and then it updates the export state. And all this is automated in code, and the admin never has to touch it. Then afterwards, and the separation is a little bit of a pain on the face of it, but it's also important because it separates that access control from just the existence of the resources. The user then says, I want to grant this instance access to this share. And again, it goes to the API server and then to the scheduler, and then the back-end code goes, oh, I need to update the exports table to give that access. And again, this is the code that we're actually working on now. It's more than just Lustre. So this model is a generic NFS re-export backend for Manila. It's not a lot of other use cases. Any environment where you have an existing data store that you want to make accessible inside your cloud can benefit from this. So we're in the process of contributing back to the community. We've already contributed some code to the Manila project, and there's more on the way. I've been working with Matthew Sanderson from NCI. I'm also working on this with the Nectar Research Cloud, and particularly thanks to Sam Morrison for assistance with that. So, can we do this better? I'd like to say yes, but right now the answer is no. For a number of reasons. There are improvements to the Lustre security model on the way. The Intel talk at the start of yesterday included a timeline that had a number of quite useful looking security model improvements. Unfortunately, none of them are really there for this use case. They can help with things, but not solve this problem. So the big one, the one that I would really like to see resolved my way, I guess, is the subdirectory mounts. I think that was scheduled for Lustre 2.9. Basically, the client sees the top of the subdirectory as its root. Great. Problem is it's implemented on the client, and that means when you've got an untrusted client, you basically can't do that. It's not usable for this context. It might be useful if you could create trusted infrastructure where you know that your hypervisor is hardened, the guests on top of it are hardened, and this is an environment that cannot run, has never run, and will not run untrusted instances. In that context, just provide a direct Lustre mount. That's fine. But in a broad untrusted cloud environment, you basically can't make use of that. If it was on the server side, so if the server was the one that was enforcing that subdirectory rooted view of the file system, then it would be good. Kerberos authentication, I've had difficulty finding out the state of Kerberos authentication and details about the way that it works. I've heard it's production ready. I've heard it's not there. In theory, it should allow us to control access to a Lustre file system based on Kerberos tokens. Manila has some support already for managing credentials, so it can manage SFFS credentials and a couple of other things. But actually making that work in this context would be would require a lot more investigation. The one that looks more promising in this context is shared secret keys. In that context, the Manila backend would become a secret key management system. So the user would request access for an instance, and then they get a secret key that would be built an instance, and would give access. Most of these things, though, end up relying on being able to squash user access to a known UID and GID. Because otherwise, if you're trusting the instance for the UID and GID information, then you're screwed. So UID and GID mapping support, which was on the roadmap, I'm not sure, but I think it was 210. It's basically a good thing, regardless of any of the other stuff. In an ideal world, my ideal world right now for solving this problem would be server-side subdirectory mounts and UID GID mapping. So, in conclusion, basically right now we're stuck with NFS gateways. It isn't the only option, but in an untrusted environment, you really need to have that server-side trusted infrastructure for mediating access. Otherwise, essentially, you're handing random people, some person in China, some person in Russia, direct access to your credentials. Providing that NFS access is technically very simple, but it's not flexible. It doesn't work very nicely in the cloud environment. Manila provides a really convenient framework for automating and integrating it into cloud, and basically making that the kind of access that users want available in a cloud way, basically the infrastructure as a service, dynamic, flexible, user-controlled way that cloud users assume. And big takeaway I would like to push out to all of the vendors and developers and stuff. Lustre really needs more server-side security features. It's not a trusted world, and assuming that it's trusted, that the world is full of trust and unicorns and rainbows, basically means that you can't do the things that researchers actually want without jumping through hoops. It'd be really nice to be able to directly mount Lustre on cloud instances. When you do, it works nicely. It's fast. It gives good access. It's pretty much ideal. The problem is you can't, because, as I said at the start, the cloud environment is inherently untrustable. Maybe if you jump through hoops, buy VMware stuff and lock things down, it might be trustable. But outside of that context, you cannot trust the cloud. And Lustre does not provide any way to insulate our big data stores. The crown jewels, really, the whole point of doing HPC from the malicious side of the